Hello. Now we go back to the resolution, of course, the solution actually, to our optimization problem. Remember, our optimization problem based on the large margin bound is the optimization problem to find, to have the support vector machine algorithm. So, of course, by solving this optimization problem, we solve the support vector machines. And we're going to see, actually, several videos to some videos, probably, I don't know, like following 5 to 7 videos. We always are going to have like something related to this optimization problem, and it's not that easy to solve it. We're going to discuss a lot on that, don't worry. So to solve this problem, we still need to give an additional step. Our additional step is, in addition to Lagrange multipliers, we need the Karush-Kuhn-Tucker multipliers. I will start with some basic concepts. We are going to discuss those basic concepts. We're going to solve like a problem. Then in further videos, we will discuss how to indeed interpret and understand the Karush-Kuhn-Tucker multipliers. Here, you guys can see I defined it as the Karush-Kuhn-Tucker conditions. Those conditions, just to list for you, they define the necessary conditions to have a solution for either a linear or a non-linear optimization problem. That's really interesting. So I can use it to understand if my problem, first of all, has a solution. Okay, it doesn't matter if my optimization problem is a linear or a non-linear optimization problem. If you don't have any idea what's like a non-linear or a linear optimization problem, don't worry. We're going to have some videos only on optimization, just to discuss optimization in more details. So it doesn't matter. You're going to see later, okay? It is more general than the Lagrange multipliers. Why? Because it allows to solve inequality constraints, not just equality, but also inequality. So it allows to solve more complex optimization problems. There is another point. It is usually not solved directly. This is quite interesting. We typically solve it numerically. This means I will not, that's typically, okay guys, I will not solve a problem in an analytical way as I did for the Lagrange multipliers before. Typically, we're going to solve using an algorithm, using a numerical approach, okay? Anyway, in this video, I just decided to come up with a very basic problem that I can solve manually, that I can analytically solve, analytically solve. Oh, sorry, I'm so tired because of, all those classes, I've been shooting all those like in a row, so it takes time, you guys know. Just a very nice example to approach the Karush-Kuhn-Tucker conditions. It is used to solve problems in two standard forms. This means that if my problem is not in this or this standard form, I can adapt my problem to make it like this or like this, okay? It is not that difficult. We can just build up those standard forms. We're going to see that, I think in this video probably. We can solve maximization problems of some optimization function f of x subject to a constraint in terms of greater than or equal to 0 and equality constraints. By equality constraints, I mean equal to 0. Or minimization problems also for a given optimization function in which my constraints are also in terms of being greater than or equal to 0. and my equality constraints, of course, equal to 0. All those equal to 0. Remember, my f is the objective function, typically the surface, as I plotted in the previous videos, okay? And we have now inequality and equality constraints. We have those, of course, maybe there are like a bunch of I constraints, those inequality constraints and those inequality constraints. Before, for the Lagrange multipliers, I only had equality constraints, okay? The first point about the Karush-Kuhn-Tucker conditions is this. The first condition is called the primal feasibility. You guys can understand the primal feasibility as I must satisfy every constraint. It doesn't matter if it's an inequality constraint or an equality constraint. So I need to satisfy all constraints. We call it the primal feasibility. We're going to see later in further videos, don't worry. That primal feasibility is related to the primal problem. Primal problem is the first problem that we find while formulating an optimization problem. In our case, our primal problem for the support vector machine is the minimization of half of the norm of vector w to the square subject to the constraints as we defined in the previous videos, okay? So the primal feasibility is basically, okay, I need to satisfy my constraints. That's okay for now. The second condition is also referred to as stationarity. The stationarity, it's not difficult to understand this. I think you guys can have a big picture. Take a look at on this. You see, I have the gradient vector of my optimization function. Here I have the gradient vector of my constraints in terms, you remember, G are related to inequality constraints. Remember, here is the same as the Lagrange multipliers. I'm solving for this. And here I have the gradients of my equality constraints. You guys can see that instead of having like plus and plus, I'm just considering minus here, instead of plus here and plus here, because they should be, and the previous formulation was using like minus on this side. When I brought here, it was plus, and here it's just the opposite. For now, it doesn't matter that. Just consider minus for now. We are going to discuss on that. Actually, this sign is going to directly depend if I am solving a maximization or minimization problem. If it's one of those, it's plus. If it's one, the other is minus. But we are going to discuss that later. Don't worry, okay? That's not important at this point. What this second condition means, it means I'm trying to find the parallel gradient vectors. I mean, I'm trying to make the gradient vector of my optimization function equal to the gradient vectors, the composition of gradient vectors of all my constraints, as in the Lagrange multipliers, in the same way, guys, same way. Take advantage of what Lagrange found when analyzing optimization problems for the equality constraints, but now using inequality and equality constraints instead, okay? The third condition tells me that I will have a bunch of me's of I. Those me's of I can go back here. You guys will see that I have some multipliers here. I have lambdas and I have me's. Those are my Karush-Kuhn-Tucker multipliers. Those multipliers are somehow working on the gradient vectors of the equality constraints. And those me are working on top of inequality constraints. So of course, those guys here, when I multiply by my inequality constraints, must provide 0. You know what is this? This is the same as trying. This is the same as trying to make some sort of correction in my inequality constraints to make them equal to 0, to force them to become equality constraints. We are going to discuss this in further videos. For now, just be happy that this is, okay, a third condition. It's called complementary slackness. This complementary slackness term is referred to the dual problem. If you guys have an idea about primal and dual optimization problem, be happy, and remember, this is related to the dual problem. For now, I'm not going to discuss that. I'll discuss later in the following videos. Just to remember, this is only for inequality constraints. Equality constraints are not, do not need to follow this rule, okay? This third condition. And there is a fourth and last condition. This is called dual feasibility. There is something really interesting here. Every problem you're going to see in the further videos, every problem can be formulated in terms of its primal form and its dual form. The primal is the first form we find to represent an optimization problem, and the dual form is, of course, the second way of representing that particular problem. While when I ensure the primal feasibility, as we've seen before when we were talking about the first condition, we ensure that in the regional space problem, the solution ensures the inequality and equality constraints. It meets the equality and inequality constraints. When we talk about the fourth condition, or dual feasibility, we are talking about a second space in which our problem, of course, our problem can be written in this second form or second space. When I ensure that every me of I, remember, me of I are the terms that the Karush-Kuhn-Tucker multipliers that I multiply by my inequality constraints. They must be greater than equal to 0. Every value must be greater than or equal to 0 for the inequality constraints. Okay? For now, this is just a condition. You guys, it's just amazing. Like, after discussing this in details, the first, the second, the third, and the fourth conditions in details, you guys are going to be impressed, I'm sure. Like, now I know why the first, why the second, why the third, why the fourth condition. That is coming later, I promise, okay? For now, just be satisfied. Okay, I know I've got like a bunch of conditions. I have to satisfy the conditions. Consider a problem. Let's solve this minimization problem. This is my optimization function, okay? For x1 to the square plus 2x2 to the square. x1 and x2 are my variables, my input variables for my problem, as you guys can see here. And my constraints are 3x1 plus x2 must be equals to 8, and 2x1 plus 4x2 must be equal to, smaller than or equal to 15. And there is something really interesting here. Just consider someone tells you that the second constraint is non-binding. We say that a constraint is non-binding. That's the same as saying that this constraint is unnecessary. It's not necessary. It's not going to affect my solution. So if it doesn't affect my solution, I can drop it. What is drop a constraint? What is make it as non-binding? is multiplying it by me equals 0. This is just to give you a very nice introduction to Karush-Kuhn-Tucker conditions and Karush-Kuhn-Tucker multipliers, guys. So I will multiply it by me equals 0. Someone told me. That's something that, let's say, an oracle or a master told me, okay, this is going to be unnecessary. So just multiply by me equals 0. Okay, to solve my problem, what I will have? I have to write it in my standard form. The standard form requires to be greater than or equal. So I will multiply this constraint by -1 and have this. It's a minimization problem having inequality and equality constraints, inequality in form of greater than or equal. Okay, that's good. Again, having my problem, I'm going to apply my first Karush-Kuhn-Tucker condition. All constraints must be satisfied. That means that this first constraint has to be satisfied. I just canceled my second constraint out because someone told me that it is non-binding. Non-binding means it's meaningless. It doesn't help me finding a better solution. So I just forgot it. So my only primal feasibility, or if I prefer, my first Karush-Kuhn-Tucker condition is I need to satisfy this constraint here. Okay, that's my first condition. My second condition, or the condition of stationarity, is the gradient vector of f of x minus. Remember, this minus here, those two minuses will be plus depending on my problem. If it's a minimization problem, it will be minus. If it's a maximization problem, it will be plus. We're going to discuss that later, don't worry, okay? Okay, going for this, I will have to solve this. This is the same as solving Lagrange multipliers, guys. Take a look. I will have to find the gradient vector for f of x. That's easy. When I differentiate this function in terms of x1, I will have, of course, 2 times 4, 8, x1, and this will be 0. That's here, okay? When I differentiate in terms of x2, I will have 2 times x2, 2 times 2, sorry, it's going to be 4 x2, and this will be 0. For x2, it's in here, okay? First term. Here I will have, okay, 0 times my constraint, my inequality constraint, so it doesn't matter, it's not going to help me. That's, actually I just inverted here, guys, sorry. Just my inversion, my bad, okay? This will be, of course, if I come up with my first constraint, which is in here, and I differentiate in terms of x1, this will be 3. Only 3. 0 and 0. Okay? 3. It is in here. And if I differentiate my first constraint in terms of x2, it's going to be 1. And here is going to be 0 and 0. That's 1 here. Okay? Of course, if I differentiate my second constraint, besides it's not applicable, I'm going to differentiate just to show you guys. Differentiate in terms of x1, it will be -2. Differentiate in terms of x2, it will be -4. Okay, I have to multiply this by μ1 and this by λ1. Those are my Karush-Kuhn-Tucker multipliers. This will be 0 because I told you, someone told me that this is non-binding. It's just unnecessary. So this will be 0. Okay, cancelling out this, making it 0, I will have this result over here. Everything must be equal to 0. Why is 0, 0 here? Because this first equation must be 0 and this second equation must be 0 as well. Okay? Now I need to solve this problem. It's not difficult to solve this problem. Take a look. I just decided to write it using a matrix form. So I just wrote it like this. 3 times x1 plus 1 times x2 plus 0 times λ1 is equal to 8. Going back, 8 times x1 minus 3. Let me see if that's the case. I just don't remember. Sorry. No, this is the first. Yeah, it's the constraint itself. Okay. I forgot to show you guys that I should differentiate here in terms of lambda 1 and of course to find this constraint, and in terms of me1 to find the second constraint. So remember, I need to solve for this system plus this constraint. This was cancelled out, but this constraint over here. This is 3 times x1 plus x2 equals 8. Take a look here. 3 times x1 plus 1 times x2 equals 8. 8 times x1 minus 3 lambda 1 is 0. Take a look. 8 times x1 minus 3 lambda 1 is going to be 0. Okay? It's going to be 0. And 4 times x2 minus lambda 1 will be 0. 4 times x2 minus lambda 1 times 1, okay, or minus lambda 1, simply, it will be 0. Okay? As simple as that. So I just got this and I decided to solve this in a very, very simple way. I have this system, okay? So I just use the row reduced echelon form. That's the same as scheduling my matrix. So I started scheduling my matrix or simplifying my matrix to find an identity matrix, as you guys might remember. To find x1, x2, and lambda 1 for this problem in which I have this A, my vector x here and my b vector over here, I just have to find my inversion over here. I have to make x equals to the inverse of A being applied to my vector b. This should be lowercase and this should be lowercase. Sorry guys, sorry, my bad. Solving this and finding this matrix, what I will have is x1 equals to 2.182, x2 equals to 1.455, and lambda 1 equals to 5.818. Okay? I'm going to carry on. Further conditions are only necessary for inequalities. Remember, the third and the fourth are only necessary for inequalities. In our case, this doesn't apply. So if it doesn't apply, it doesn't matter. I don't need to consider the third and the fourth conditions. I can go for my solution without considering both the third and the fourth Karush-Kuhn-Tucker conditions. Okay? So my solution, of course, in this particular scenario over here is given by this x1, this x2, and this lambda. My solution is here. Okay? I'm going to go for a different problem now, guys. Try to solve this problem. This is a completely different problem. And now we've got two inequalities. But this is not in the standard form. Take a look here. I need to rewrite this constraint to be in greater or equal form. So I need to put it in the standard form like this, multiplying it by -1 and making it like this. Okay? So minus plus plus minus, it will be plus minus minus plus, and this is going to change this operator. Okay? To start solving this, I will have, of course, to consider the first Karush-Kuhn-Tucker condition. What is the first Karush-Kuhn-Tucker condition? The first condition is I must satisfy my constraints. I must satisfy my constraints. You know what's interesting? I can just at the end, I can go for the second condition, find the values, go back to the first condition and verify if my constraints were satisfied or not. I don't need to assess the first condition at first. I can assess the second at first and then go for the first condition later. This is a minimization problem. Again, remember, this must be a minus sign. We are going to discuss on that. We're going to understand why this is minus, but that's going to take some time, believe me. The second condition is stationarity. That's the same as writing this way of solving our Lagrangian problem, as we've seen before. I think you guys remember that, right? Of course, oh, you know what's funny? Here it should be like the gradient, here it should be the gradient, and here should be the gradient. Sorry guys, I forgot to add the gradients here. My bad, once more, just remember, okay? So how can I solve this? Of course I can solve like this. I have the gradient vector for f in terms of x1, x2, and x3. And the gradient vector of my constraint number 1 and my constraint number 2. Of course, if I want to detach my gradient vector, I can see my derivative in terms of x1, x2, and x3, x1, x2, and x3, x1, and x2, and x3, and all three together compose my gradient vectors, just to remember, okay? That's simple, and that comes from calculus. So when I differentiate my function in terms of x1, take a look at my functions here, in terms of x1, that will be 2 times x1. Take a look, 2 times x1. When I differentiate my function f in terms of x2, that will be 2 times 2 for x2, as shown in here. When I differentiate my function f in terms of x3, that will be 3 times 2, 6x3, as shown in here, okay? First constraint, differentiating in terms of x1. First constraint in terms of x1, that will be 5, okay? To be 5, as shown here. First constraint in terms of x2, first constraint in terms of x2, minus 1. Minus 1, as shown here. First constraint in terms of x3, first constraint in terms of x3, that will be minus 3. Minus 3 over here. Second constraint in terms of x1, that will be 2. 2. Okay. Second constraint in terms of x2, that will be 1, as shown here. And second constraint in terms of x3, that will be 2. Okay, 2. Perfect. All of those equals to 0, remember. Okay? Remember, if I want to bring these two terms to this side, and these two terms to this side, and these two terms to this side, I'm just making the gradients parallel. Okay? Minus sign related to minimize, plus sign to maximize. Okay? So if it's minus here, it's going to be plus on this side. And if it's plus here, it's going to be minus this side if I'm solving a maximization problem. Remember, just go back to the other videos and remember that I said, oh, this minus in front of lambda, it's not really important for now. Actually, that minus or plus is related to solve a minimization or a maximization problem. And I need to consider my constraints. My constraints now are considered for the equality. The first is equals to 3 and the second equals to 6. Take a look. I can't just forget about the inequalities and solve for the equalities. Okay, that's quite interesting. Again, those are my Karush-Kuhn-Tucker multipliers. I can solve that. How can I solve the same? I can build up a linear, actually a system of equations and solve this linear system. By solving the linear system, I find x1, x2, x3, me1 and me2. And there is something quite strange about me1. I don't remember, if you guys remember. This guy can only be greater than or equal to 0. It cannot be negative. let's discuss what happens. This actually violates one of our conditions. It violates the condition, the fourth condition, in which every me must be greater than or equal to 0. You know why? Actually, this happens whenever a constraint is non-binding, whenever a constraint is not significant for my problem, is not relevant for my problem. So what I should do, I should cancel out my first constraint. Here, I just decided to plot for you guys the surface I have for my optimization problem. This is my first restriction. This is my second restriction, or constraint if you prefer. Those directions are the gradient directions using a small triangle, okay? You guys can see that I don't touch my constraint number 1, just constraint number 2. That's why me for number 1 is going to be negative. It means this constraint is non-binding. It's not relevant for my problem. So what I should do, I should just cancel this constraint, because this constraint is enough to solve my problem. This constraint number 2 is enough. If I had the point, the blue point, which is my solution over here, both constraints would be relevant. So I would have a me value 1 and 2 greater than or equal to 0 for both. Actually, greater than for both. That's quite interesting. If you want to understand this, just watch this video. This video has like more information. Now we can solve for the first condition, having me equals 0 as homework. That means we are considering the first condition as non-binding. That means the first condition is not relevant. Actually, I bring the solution over here. If you guys want to see, I remember, yeah, I think I brought this. No, I didn't. Oh, sorry guys, you have to solve it. Doesn't matter, you guys solve it. Just some additional points here. The Karush-Kuhn-Tucker conditions were originally named after Harold Kahn and Albert Tucker. Okay? They were the first to publish the conditions in 1951. However, there is a guy called William Karush, there was actually, who published his master thesis in 1939 with the same conditions. That's why nowadays we call it like Karush-Kuhn-Tucker conditions, because those guys over here were the ones to be famous at first, and then later someone found that William Karush was the first, in fact, to publish the conditions. Okay? Actually, it should be called the Karush conditions only. just kidding. Here, I just propose you guys some additional problems to solve. Consider this problem, just put it in the standard form again, remember? Okay? And solve it. And here I suggest some additional videos so you guys can click on the links or type those links and watch those videos. That's really, really interesting, okay? All those videos are really nice to understand the Karush-Kuhn-Tucker conditions. For now, that's all. What's going to happen now is the next videos, we are going to go into the details of optimization. Not in such details like in a course about optimization, but I can tell you that we are going to learn or see once more optimization, just to refresh your memory and solve our support vector machine problem. If you guys have no idea about Lagrange multipliers, about Karush-Kuhn-Tucker conditions, or about optimization problems, don't worry, we're going to discuss in the following videos. If you guys know those concepts, try to get those concepts back in your brains, your minds, because it will help a lot, okay, in the next videos. See you guys.